All right. So we're getting ready to start talking about forces. And essentially, what we've been doing with kinematics is talking about how things move through like projectile motion or even just one-dimensional motion. So the idea with forces is essentially we're going to start talking about why things are moving the way they do. So I did give you the one whole chapter from the textbook we're using right now to read that corresponds to lecture 5.1. There wasn't a lot of math in it. It was just a lot of descriptions and ideas. So I'm going to very quickly go through that and just give a broad overview. If you don't quite get something in this lecture, that's okay, because we'll see a lot of this stuff again in the future. So right now, this is just to sort of plant the seed in your mind, get you thinking about this, and then we'll hit it in a little more detail in the future. So essentially, Isaac Newton here, he developed his laws of motion in the 1600s, and he did it so well. He didn't just pull them out of thin air. He had some help from previous people, Aristotle, Galileo, but he sort of formalized them with math and made them more rigorous and robust. And it turns out we're actually still using his laws of motion today, which is pretty impressive given that they're 400 years old. So again, we've talked about kinematics, how things move, and how we can model that mathematically. We're getting ready to start talking about dynamics now. This is the why things move. And when you put these two things together, kinematics plus dynamics, you essentially get mechanics. And this is just the science of motion. If you wanted to do this like at a senior level, like in a senior level physics course, the class you would take would likely be called classical mechanics. I'll write it just because. So the idea here is that in classical mechanics, you're studying how things from small things like bricks falling off of a building up to the planets, how they move. It's all about being able to look at motion in a mathematical sense. Now let's discuss essentially a description of a force. I'm pretty sure I probably said the word force at some point in this course, but now let's actually put a definition to it. So when we're talking about forces, you have to remember that there is an agent which is going to act on an object. So it's an agent-object interaction. So we have agent, we have an object. And essentially, if we can jump down for a moment to this fourth bullet point, this is actually Newton's third law. Forces are essentially interactions between two objects, agent-object. And that's actually just Newton's third law, which we will talk about later in detail, but for now, just know that it's the third one that he came up with. So forces are, a force is a vector, so we can draw a direction that the force is happening, and it does have a magnitude. A larger force will have a longer vector, a smaller force will have a shorter vector. So a force is a vector. There's two different types of classifications of forces. You can have a contact force, so when the agent and object are actually touching each other, or you can have a long range force. So the agent and object are far apart, but they're still influencing each other somehow. Okay, so you can have contact or long range. So let's briefly just talk about how to represent a force as a vector. So we do have whatever object is being acted on. We can represent that as a particle. We're going to use the particle model here, just like we have been doing. So in this case, let's say this object, whatever it is, let's say I pushed it from behind. Okay, so even though I pushed it from behind, I'm always going to draw the tail of the force vector on the particle, okay? So even though it is coming from behind, and this vector here is the force that I'm applying, I always start from the object and draw the vector in the direction of the force, okay? So it's got to be in the proper direction and with a length proportional to the size of the force, okay? So that proportionality has got to be there. So the length is proportional to the size of the force. So it looks like I pushed this pretty hard because that vector is pretty long. That's the general idea. And of course, just with any vector, you want to give it the appropriate label. And we usually, but not always, we usually apply just a capital F as a force to some vector. If we look at these three examples from the text down here, it might be a little hard to read, but here we have a box in three different situations. And in all three situations, the box is our object, 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 object. But we do have three different agents that are acting on this box. So in this first example, the rope is the agent. Okay, I'll underline the word rope, but it is a little small. The box doesn't care that there's a person over there. We're just thinking about all of this from the box. So the box just knows that there's a rope attached to it, and this rope is applying a force. Now this is a pulling force, so it makes sense that the vector is on the same, is like pointing in the same to the same side as the pulling force. It points in the direction that the box is being pulled. It looks like it's a pretty hard pull because it's a long vector comparatively. Now let's compare that over here to the other one. So we have a spring. Okay, so here the spring is the agent, and this is actually a pushing force. So you'll notice that even though this is a pushing force, we're not, I'm going to do this in blue, even though this is a pushing force, we're not drawing the vector to the particle. Okay, the vector gets translated over, so its tail is always on the particle. So this is a no, even though it is a pushing force. Okay, so let's see. These over here, these first two that we talked about, these are contact forces. Contact. Ooh, that's really bad. Let me try that again. These are contact forces. Okay, so that just essentially means that the agent, in this case the rope and the spring, and the object, the box, they're actually in contact with each other. Now, let's talk about this other long-range force over here. So this is a long-range force. So this is the box is falling, clearly. Okay, so it's falling toward Earth. And the way that is doing that is essentially the force due to gravity. Okay, so we've talked about acceleration due to gravity. That's the how is it falling? Well, how is it accelerating? Well, G. But now the why does it accelerate like that? That's what we're looking at now. So the why is the force due to gravity, not how much, which is the acceleration due to gravity. So in this case, Earth is the agent, and you'll notice that they're not actually touching each other, right? So there's no contact, but still the object and the agent are interacting. Okay, the Earth is going to pull with gravity. It's going to pull the box down. So as far as summation of forces, generally when you talk about forces acting on an object, you have one object, but there could be several forces acting on it. Okay, so in the case where there's several forces, we could talk about what each one of them individually is doing, but it turns out we can actually add up all of these forces. So if there's 27 different forces acting on one object, we can essentially do vector addition or algebraic addition of vectors. We can add up all those forces, and that gives us a net force. So one big force, all those 27 forces can be represented by one vector, one force. Okay, and that's our net force, and we essentially just represent it as F sub net. Okay, so a little subscript there, net means all of them added up. So I assume you all have seen this summation vector, or sorry, this summation symbol is just Greek letter sigma. So this just means a sum. The I equals 1 to n tells us how many of these are going to add up. So the reason it's n is because we generalized it. There could be 1,000 forces, so n would be 1,000. Or there could be 3 forces, then n would be 3. So the whole idea is that to get the net force, we just add up all the individual forces acting on an object. Some other words that you might see is for this exact same thing. The net force could be called the resultant force. And the way some people might talk about it is a superposition of forces. That just means they're all added up. They're all on top of each other, okay? So I guess we could say this is layered on top of each other. So that's essentially just like when you do the tip to tail method, you put them all like, you know, not the tip to tail method, when you put, when you add up all your x components and all your y components, all those vectors sort of collapse into one summation vector. That's the idea here. That's the superposition part. So just to give you an idea, you can look over here on the right. We have some box. So here again is our object. And we have two forces being applied on it. We have someone pulling to the like upper right. Okay, so we have one force vector going this way. Looks like this is F1. And we also have someone pulling straight down. So this is F2. Okay, remember these are vectors, so they need vector hats. So we can take these two vectors I've drawn and put their tails at the origin. Okay. So here, this is our box now. It's represented as a particle. All right. Now we just add these two vectors together. We can do that with the tip to tail method. Okay. So let's say I take vector, I don't know, vector 2 here. Let me switch this to green. So let's say I take vector 2 and then I slide vector 1 down and add it to it. Okay. So here's vector 1. So you'll remember when I do the tip to tail method, I just connect from the origin where I started, and then I connect to essentially where I've ended up after I put all the tips and tails together. Okay, so here's my resultant vector. Okay, so that's my F net. And you can see, and it's going to point in the direction you would expect. Like if they were to really yank on this box, you can sort of see it shifting to the right and then down a little bit. Kind of this direction. Okay, so we have a whole list of forces here. These are some forces that are discussed in more detail in the book, but I'm just going to hit them all very briefly. So we do have several, and this isn't necessarily all of the forces. This is just a broad overview, mostly dealing with classical mechanics, which is essentially this course. So in terms of gravity, the gravitational pull of a planet on an object is essentially the gravitational force. So when you're talking about gravity, generally you're going to talk about a whole planet. So this is the pull of a planet, and it's on an object on or near the surface. So in this case, the agent. This might be a little hard to see, so I'm going to change colors. Agent, much better. Okay, so the agent for the gravitational force is the entire planet. So in this case, all of Earth pulling on the box over here on the right. So gravity does act on all objects, whether they're moving or at rest. So let's state the obvious here and just say gravity is always on. Okay, and that's true on any planet that has a lot of mass. So how we represent the force due to gravity is essentially just capital F with vector hat, and then a sub G here, a subscript G for gravity. And then, of course, gravity always points vertically downward. So even if we have like a really weird ramp situation going on, gravity always points straight down. So again, here's our object, here's our agent, which is the whole Earth. Okay. Now, Clearly we're neglecting air resistance on this box because we don't have an arrow pointing up to show like the force due to air resistance. So we'll talk about that later. Right now, just know that we're representing the box as a particle. Box as particle. And then gravity is just the force pulling it down. All right. So the next would be the spring force. Make sure I didn't skip one. Yeah. So next is the spring force, and that essentially can be either a push or a pull. And you've seen this in a previous slide already. So the symbol we use for the spring force is just F sub SP for spring. And it doesn't matter whether the spring is pushing or pulling, the tail of the force vector is always placed on the particle in the force diagram. So remember, the tail is always on the particle. So you can see here in the case of a push, okay, so we're pushing in this direction. That does not mean we draw the vector on the left-hand side and point toward the particle. We always draw from the particle the direction the force is being applied. And then, of course, we have a pull over here. Same thing, we're drawing the direction this box is being pulled. Tension is just essentially when you have a string, a rope, or a wire, and it's tied to an object, and you're yanking on that string. That's going to cause a tension force, and we actually represent tension by T, capital T. Notice this is not the period that we've been talking about in circular motion. Time, period, not a vector. Tension is a vector. So the direction of tension, this is pretty important. The direction of tension is always in the direction of the string or rope. Okay, so you can see over here the sled example. Someone's pulling this sled with the rope. It's pointing this way. That means our tension vector has to be pointed at the same angle. And clearly they're not pulling very hard because the tension vector just doesn't look to be that long. We have no reference for like how hard exactly this is. It's just that we've seen longer vectors in this lecture, so maybe they're just barely pulling it. So essentially on a molecular scale, the tension in the rope is supplied by all those molecules. So all the molecules in here, all the molecules of the rope, they're sort of held together by these molecular bonds, and those molecular bonds kind of act like springs. So if you want to get really super technical and annoying, you can say that, well, the tension force is really just a spring force. Technically true, but when we zoom out and we think about everyday objects, we don't have to think about the molecules, and we can just call it a tension force. But just be aware that a lot of the forces we talk about are really just from molecules acting like springs. Okay, so this next one is a little weird. It's the normal force. So in this situation, here we have an object sitting on a table. Okay, well, our object is a textbook over here. So we have an object sitting on a table. It is under the influence of gravity because everything always is when it's sitting on Earth. Okay, well, even though this gravity is acting on it, the object is clearly not accelerating downward. So why not? Why isn't it traveling through this table, through the ground, and then stopping at the center of the Earth? Because it does have the force of gravity acting on it. Okay, so I could draw that in here. So here's my particle, here's my vector, so that this is Fg. Okay, well, there's my force due to gravity acting down on the book. So this tells me something. It's not moving, nothing's happening. So the table must be applying an upwards force to cancel out gravity. Okay, so this is an important one here. The fact that this thing is not moving and it's kind of sitting in equilibrium means that there's got to be something canceling out gravity. Okay, well, that's actually the normal force. Okay, and mathematically speaking, normal just means perpendicular. And hopefully you guys remember that perpendicular just means essentially at a 90-degree angle. So it's just pointing always directly up from the table and is perpendicular normal to the table. That's always the case. The normal force is always perpendicular to whatever surface we're talking about. It's being touched by an object. Again, The normal force is supplied by the molecular quote-unquote springs of the surface. So you can see in this little inset here, the book has the force due to gravity pushing down on it, but all the wood molecules, they act like springs, so all the springs are pushing back against it, and that's essentially canceling out the gravity. We do represent the normal force by a lowercase n for normal. I don't know why, that's just convention. I didn't make these rules. I know they're kind of weird. But let's look at these other two examples. So if you reach your hand out, push against a wall, like this lady's doing, essentially this right here, this vector is your normal force. You'll notice that it is perpendicular to the wall because that's the surface is being interacted with. So as always, the normal force points perpendicular to that surface. So as the lady pushes on the wall, the normal force pushes back on her hand, and the normal force is what's essentially keeping her from just like bursting through the wall and going into the next room. Now, obviously, if you push hard enough, you can overcome the normal force in some instances, like a thin paper wall, or you know, even a brick wall if you use a sledgehammer. But when you're modeling these things, you have to understand that the normal force is generally going to cancel out whatever forces are being applied up to a point. And even if you're looking at like an angle like this frog here, where that's just sitting on this ramp, the normal force does point at a 90-degree angle perpendicular to the surface, and that's always the case. Right, there's also some frictional forces. So friction is also exerted by a surface, okay? But this is where it's a little weird. So normal force always is perpendicular, but the frictional force is tangent to the surface, okay? So now we have something tangent or parallel. Now we have a frictional force that is running along the surface instead of 90 degrees away from it. Again, friction arises from those atomic interactions between the object and the agent. So essentially, it's just you have your molecules and your atoms in one object and then the other, and as they scrape along each other, that interaction is what's going to resist the motion. So this is really just atomic interactions. The rougher the surface, that just means there's more chances for those atoms to interact. They're forced into close proximity. So, you know, just more surface area and more chances for these things to rub against each other on a really rough surface. Now, there are two types of frictional forces. We have kinetic friction. Okay, so this is essentially as an object moves, kinetic friction, hence the name kinetic, because something's moving. Kinetic friction will oppose the motion. Okay, so this is an object sliding along a surface. This is after something's been moving, like right here, this kid on the sled, you'll notice there's a velocity. So we know this kid's moving. Now, the kinetic friction opposes the motion. That's always true. So our kinetic friction is always going to point in the opposite direction. So since we have our velocity pointing to the right, we know our kinetic friction is going to be pointing to the left. Okay, and we do represent it with a lowercase f with a subscript k for kinetic friction. Let's see, and this is only when moving. Now the other one you may be able to guess is static friction. And static friction is the thing that keeps something stuck where it is. If you ever tried to like push a refrigerator, well, it's really heavy. Those molecules are really being pushed together on the surface that's trying to push it across. So that friction, when it's not moving, but you're trying to get it to move, that non-moving friction is actually static friction. And that's essentially that keeps an object stuck on a surface, and this is the thing preventing motion. And we represent it with a f, lowercase f, sub S for static friction. So you'll notice here this frog. Well, it would make sense that the frog, what it would want to do, it would want to slide down the ramp, right? Because gravity, we have gravity acting down. So we do have this force due to gravity. So gravity's wanting to pull it down to the bottom of this ramp, but it's not sliding. I mean, it's a frog, it's sticky. So that stickiness is the force of that stickiness is represented by the static friction here. Okay, so that's of course pointing up, and it always opposes the perceived motion, the motion we would expect. We expect to go down the ramp, so this vector's got to point up the ramp to cancel that out. Okay, so this is only when stationary. Yeah, so it looks like I already hit this one bullet point, but just again, kinetic friction points the opposite direction of motion, whereas static friction stops the motion we would expect before it even gets started. All right, with drag, we probably won't do a lot of drag. I do like to incorporate one or two problems on problem sets that do include drag, just because it gets really fun mathematically. So this is essentially the resistive force in a fluid, and it's just called drag. So this can be an object moving through water or the atmosphere. So it turns out that the atmosphere is, you can at least model it or approximate it as a fluid. So when we talk about drag, it can be a boat in water or it can be in the atmosphere. So the drag force is denoted by capital D. And like friction, it points in the direction opposite of motion. Okay, so you can just think about drag being friction that's not on the ground. But for heavy objects that are sort of condensed and compact, and they don't move super fast, the drag force is relatively small. That's why we usually ignore it in most of like the problem sets, or in most of our discussions of kinematics and force problems. We usually don't talk about it much. So here the idea is, since like these leaves falling are lightweight and they're not super condensed and compact, they're going to experience a drag force, even though right now they all are experiencing the force due to gravity. Gravity is going to be pulling them downward, but the drag force is going to be resisting that. Almost the last one. So we have thrust, which is a contact force, believe it or not. It's a little weird to think about, but thrust is a contact force. So the agent is the exhaust that pushes back on the engine. And so we have the agent is the exhaust gas, and it pushes back. So the idea is that you push out so much exhaust gas that those molecules sort of all bump into each other, and then that gives you kind of a quote unquote solid surface to push against. And that's the thing that the rocket is pushing against as it moves either through the atmosphere or through space. So that's why we sort of think about it as a contact force, just because all of that gas is compressed. It sort of gives you a little springboard to push off of. So this is actually an application of Newton's third law of motion, the whole equal and opposite reactions. You've got your push against the gas, and then the gas is going to push back, gives you sort of that springboard, and then launches your rocket. So we don't have a special symbol for that thrust that the rocket gets, but we just call it F sub thrust. Okay, so this is thrust. This is Newton's third law, or at least an example. You can see from the picture here, this is just thrust points upward, even though we do have gravity pointing downward, or force due to gravity pointing downward. So the idea, what you want to happen, is you want your thrust to be greater than your force due to gravity. Obviously, if that's the case, if your thrust is bigger vector going up than down, your rocket will actually get off the ground. Now we do have electric and magnetic forces. All of physics 2 pretty much is dedicated to these types of forces. So we won't talk about this in Physics 1. But these are long-range forces, and these forces do act on charged particles. Just be aware that they're there. If I get super creative, I might try to incorporate these somehow into a problem set problem, but I doubt I will. But just be aware that they're out there. They're like gravity. You've got distance between two things that are interacting, and they are long-range forces that do exist. Okay, now we've talked about a buttload of forces. Let's talk about how we can identify them in problems. So this is a little more practical. So what we want to do in any force problem or any force situation that we're looking at, we want to identify the object of interest, okay? And like always, we want to draw a picture of the situation. So once we know what to draw a picture of, we'll draw that picture. And then once we have the picture of the situation, we essentially just want to draw a circle around the object. Okay, so draw a closed curve. Now, once we have that circle around the object, that's how we can identify where the forces are coming from. So we'll travel around the edge of the circle, and then we just note where the objects touch, where other objects touch the object of interest. Okay. So we just locate every point on the boundary where other objects touch the object of interest. Don't worry, we're going to do like 2 or 3 examples of this. Just get these steps down in abbreviated form, and we'll go through them multiple times. So once we've traveled around our enclosed circle, we're going to name and label each contact force. Once we get all the obvious ones, sort of that are breaching our circle around the object, once that's taken care of, we're going to name and label each long-range force. And once we've done that, we know the physics of the problem, the physics is done, everything else after that is simply mathematics. Okay, so let's do these 6 things. In this one example, it's pretty easy. It's just a bungee jumper that has leapt off of a bridge and is nearing the bottom of her fall. So what forces are being exerted on the bungee jumper? Okay, so all we have to do to answer this question is just identify the forces. Okay, so we get to stop after our first step, visualize. Okay, that's the only thing we need to do. Now, step number 1 from the previous slide, we identify the objects of interest. Well, it's the bungee jumper. Okay, so it's the jumper. Well, we done that. We identify the object. Now we draw a picture of the situation. Luckily, the textbook's done that for us. Okay, picture done. Now we draw a closed curve around the object. Okay, so that's our red line here. Okay, well, that's done. Once we've done these 3 obvious simple things, this is where it starts getting a little tricky. So now we essentially go around the edge of this circle that we've drawn, and we locate the points where other objects are touching our object of interest. Okay, well, it turns out it's just the rope. That's the only thing outside the circle that's touching our object. For this example, it's just tension. Okay, well, step number 5 is name and label each contact force. Well, we did that. Tension, done. So the force exerted by this cord is, of course, the tension force. All right. Now, the last step is the one that may not be so obvious. This is where we label the long-range forces. And obviously, we're assuming this lady is bungee jumping on Earth. So the force due to gravity, so gravity is going to be pulling her down. That's the long-range force. It doesn't breach our circle that we drew, our closed curve, but it is there and it is acting on her. So that was it. We've done those 6 steps, and that let us identify the forces. So you can see that there's just 2 forces. There's tension pulling up and gravity pulling down. Okay, let's do the same thing again, but with a little harder example. So here we have a skier that is being towed up a snow-covered hill by a tow rope. So here's some key words: snow-covered, probably means a little bit of friction, but not a lot. It doesn't say frictionless, so we're going to assume that there's a little bit of friction. He's actively being towed up the hill, so that means that there's some motion. And then there's also a tow rope, so that means there's going to be some tension. Okay, so here's a question. The question is simply, what forces are being exerted on the skier? Same process again. Identify the object of interest. Well, we identified the skier. We draw a picture. That's a nice picture, better than I could ever draw, straight from the textbook. Okay, third, we draw our closed curve. I'm calling it a circle, even though it's not mathematically a circle. So we've drawn our circle. Now, 4 is where it gets a little tricky in this problem. This is where we go around the edge and look for all those interactions. So here we have 2 points of interaction. We have, of course, tension from the tow rope here. And then we also have this interaction, this agent-object interaction of the ground, okay? So the tension up here from the tow rope, I'm going to switch to green, I guess. So we know we have tension, the tow rope, 1 force, but there's actually 2 forces associated with the ground down here. Okay, so we have kinetic friction. Now remember, kinetic friction always opposes the motion that's happening, okay? So we know that kinetic friction is going to be pointing in the opposite direction of the motion. And we also have the normal force. She's interacting with the ground. She's got some amount of her weight, even though she's on a ramp. Some amount of her weight is still pushing into the snow there, pushing into the ground, which means there's going to be a equal opposite force. So there's going to be the normal force pushing up. Still don't know exactly how I'm to draw these vectors because we don't know any actual numbers, but even if we don't know the values, we still can include them just by drawing them, okay? So we know that our normal force is acting perpendicular to the surface. Now let's see. I think that's everything. I've named and labeled each contact force. Got them all, normal, kinetic, tension, great. Now the last step is just identify and label all the long-range forces. And the only one that I can think of is just gravity. Now it's important to remember that on this lady, gravity, even though she's on an angle, she's on an inclined plane here, gravity always points straight down toward the center of the Earth. Okay. So I think those are all the vectors that we have. They're kind of all over the place, and we'll deal with that later. But right now, the point is to just identify them, get them down on paper. All right. We're going to switch gears here, and we're going to essentially do a little bit of a thought experiment. So the engine of a car provides a force F, okay? And this is, in general, we're going to say every time you get your car and you take off from a stop sign, we're going to get this force F, okay? And it propels the vehicle forward from a stop. You notice that every time you apply this force F, you get some acceleration, like from a stop sign or a red light, okay? So we're applying force F and we're getting acceleration A. However, when you take a friend with you, the acceleration is now half A. When you apply that same amount of force, when you try to take off from a stop like normal, you notice that you get less acceleration. Those of you that are driving have probably noticed this when you have more people in your car, which I'm sure you all have rationalized. There's more mass, so the magnitude of the acceleration is going to be smaller. You got to move more stuff with the same force from the engine. The engine didn't get any bigger. So with the same force of the engine, you're moving more stuff, lower acceleration. Now, let's say you're driving 4 of your friends around to dinner. So there's 5 of you in the car. So you notice that you have 5 people in the car, which reduces your acceleration by a lot. So when you apply that force from your engine to the wheels, the same force vector, you notice that even though the same force is applied, your acceleration is decreased considerably to just 1/5 the acceleration. So clearly there's some sort of relationship between an applied force and the amount of mass that the force is expected to move and how it does that. So that's actually Newton's second law. Okay, so an object of mass m, so how much of the object is there, when forces are applied to it, it will undergo an acceleration, just like when the mass of all the people in your car have a force from the engine applied to it, it's going to have an acceleration. Okay, this is actually Newton's second law right here. So it's essentially the amount of force that you have acting, the net force. Now, this is the sum of all the forces. So the net force acting on an object is distributed across the mass of the object. That's the division, divided by mass. Okay, so that ratio, the amount of force distributed over that mass, that ratio is going to tell you how much or how little that object is going to accelerate because of that applied force. Okay, so we have this force distributed across mass. An object, essentially the object will accelerate in the direction of the force vector. So if you have a tiny mass, big force, lots of acceleration, small force, giant mass is going to barely accelerate. So an object only accelerates when a force is applied. And while it's applied, as soon as you stop applying that force, you stop accelerating. Just like when you take your foot off the gas pedal when you're driving, you instantly stop accelerating. So let's look at this previous example where we had these two ropes. So I think last time we were talking about this object, this box, when we yanked on these two cables, these two ropes, we said the box is going to move sort of down and to the right. Well, that's actually the direction it's going to accelerate. And you can see from the vector summation here, the acceleration, so the box moving from rest to some final speed, is going to be in the direction of the net force. And we can actually represent this whole thing mathematically right here, just by saying, well, F net is just the two tensions added together. Okay, that goes in our numerator. And we just divide by the mass of the box. Okay, so this is just the mass of the box. Really, what you're looking at is essentially it's the net force multiplied by some little number out front. So you're taking your force vector F net and then you're scaling it by n. That's all that's happening. The 1 over m, the mass, just tells you how long that force vector is going to be, and when you scale it, that's your acceleration. So what are the units of a force anyways? So we have a force, which is, we've seen from Newton's second law of mass times an acceleration, right? So we're just going to take this A equals F over m and rewrite it. You'll probably see it this way if you do some like extra Googling or studying for this class. You'll see F equals ma. That's Newton's second law. So that's just a mass times an acceleration. Okay, but we know the units of mass, at least SI units, those are kilograms, and we know the units of acceleration. That's meters per second squared. So when we multiply a mass times acceleration, we also multiply those units together. Okay, so when we do that, we get kilogram meter per second squared, which I've written out here, kilogram meter per second squared. That's literally the units of a force, is kilogram meter per second squared. Luckily, we call this, we combine these units and we call it a Newton. Okay, so it's called a Newton. So notice this is a secondary unit. That just means it's derived or a combination of other fundamental units, because the other ones, kilogram, meter, and second, those are all fundamental base units. So a Newton is actually, I think, our first unit that we're talking about where we've actually combined units to make a more complicated one. So force is measured in newtons. So that was Newton's first law. I'm sorry, Newton's second law, which is F equals ma. Now let's look at Newton's first law. So we got to here basically from Aristotle. Aristotle, his first thought was, oh, the natural state of anything on Earth is to be at rest. Okay, so that's how everything wants to be. And then you have to do something to it to make it not be at rest. Well, Galileo followed up with that and found that an external influence or a force is needed to make an object accelerate. Otherwise, the natural state of an object is uniform motion. Okay, so here Galileo almost has Newton's first law. So almost Newton's first law. NFL, Newton's first law. Nice. Okay, so this is almost Newton's first law. But Newton came through and added a little bit to it, formalized it, cleaned it up. So now Newton's first law says an object at rest will remain at rest. So a static object remains static. And an object in motion will remain in motion, dynamic. Okay, so a static object remains static, a dynamic object will remain dynamic in a straight line if the net force on the object is 0. So if F net equals 0 newtons. That does not mean there's no forces. We could have 1,000 forces acting on an object, but if they all cancel each other out, if we add them up and get 0, this still applies. So we have this static situation here. Okay, so here's an object in static equilibrium. This dude's standing there. His velocity is 0. His acceleration is 0. Done. Newton's first law. Object at rest stays at rest. Now, let's check out this other one. So this dude is on a skateboard and he's moving, but he's moving at the same speed at all times. You can see that here in his vectors. They're all the same length. It's even noted that his acceleration is 0, so his speed is not changing. Okay, so essentially what's happening down here in this bottom one is all the forces, like the friction force, maybe, I don't know, there's a wind blowing him, but all the forces, when you look at them and sum them up, they equal 0, even though forces could be there. So the idea is that if he can keep that situation, if this guy can keep going with all of his forces equal, he'll never stop. He can go from here to Canada. But as long as those forces acting on him all, for some reason, cancel each other out, he's going forever. So you can actually see that with Voyager 1. This is the most distant human-made object from Earth. JPL, we actually manage this at JPL, manage the data interactions and downlinks and stuff. It's 161 astronomical units from Earth, and because it's like so far out of the solar system, there's not really any gravitational forces. I mean, there are, but they're so small. So really, when you think about it, there's not a lot of forces acting on Voyager 1. So since the forces are almost 0 on Voyager 1, because it's outside the solar system, it's going to continue forever in a straight line. I should include that. Straight line. And it's going to continue at pretty much the same speed forever in a straight line because there's nothing there to change its velocity. There's nothing there to cause an acceleration or deceleration. So this is the whole idea of Newton's first law. Just a little bit more about Newton's first law. So essentially, mass can be thought of as the amount of inertia that an object has. And then an inertia is essentially just the tendency of an object to resist accelerating. A refrigerator, lots of inertia, hard to push. A leaf on the ground, you could blow on it just, and then it takes off. That's not a lot of inertia. That's a small amount of inertia. So mass is essentially related to inertia. Inertia is the amount of mass, that kind of thing. Again, a force, which we've defined now with Newton's first law, is what causes an object to accelerate. So now we can talk about the thing, the cause, the how, the why that an object is actually accelerating, going through kinematic motion. So Newton's first law defines a force, right? From this law, we can tell what a force is. Something that disturbs equilibrium pretty much. Newton's second law describes the response of an object to the force. Okay, so here's the describes how an object moves when a force is applied. And then Newton's third law just sums up the whole object-agent interaction in terms of two things interacting with each other. So this is just describing the interaction. Last thing, maybe second to last thing, inertial reference frames. So Newton's laws are only valid in inertial reference frames. And that's essentially any frame of reference where Newton's first law holds. Because there's actually some situations where Newton's laws break down. That gets really complicated mathematically, and we won't really deal with that in this course. But just keep in mind that, you know, there's got to be some special situations where you can actually use Newton's laws. So if we consider figure A, we have a ball that's placed on the ground when there's of the aircraft, on the ground of the aircraft, when this aircraft is moving at a constant velocity. Okay, so it's not speeding up, it's not slowing down, we're at cruising altitude. If you set a ball down, like right here, well, that ball's not going to move, right? It's just going to sit there where you put it. No big deal. So this agrees with Newton's first law of motion. An object at rest stays at rest, you know, unless acted on by a force. Now, suppose we do the same thing, except we do this when the aircraft is getting ready to take off and it's going down the runway and speeding up. So in this case, in figure B, there we go. Sorry about that. So in figure B, there's no apparent, let's see, in figure B, this ball, when we set it down on the ground, and while we're accelerating it, it rolls backwards toward the back of the plane. But now the question is, what is the force that causes that? Okay? So there's no apparent object-agent interaction that's actually pushing this ball to the back of the plane. So the question is, why did that happen? Well, we know that there's no mystery force pushing it. So we know it's really just happening because the ball wants to stay at rest because of Newton's first law, but the plane's taking off, sort of moving away under it, which is kind of giving the appearance that the ball is moving to the back of the plane. It's kind of weird to think about, but essentially this situation is not an inertial reference frame just because we have this mystery force. This ball is accelerating, or it appears to be accelerating to us, even though there's no force acting on it. So if our coordinate system is riding along on this plane, if our coordinate system is riding along on the plane, this is not an inertial reference frame, just because we have these really weird mystery accelerations where we can't identify an object-agent interaction. So in both scenarios, a coordinate system outside on the ground would actually be an inertial reference frame for both. So if we plopped a coordinate system down here, this would actually take care of it for us, and that would give us an inertial reference frame in both situations. All right, let's put this all together in two quick examples, and then we can call it a day. All right, so now we're going to talk about a free body diagram, which is essentially just a pictorial representation of a problem and the forces acting on the object in the problem. So this diagram shows all forces acting on the object. So to construct a free body diagram, we want to identify all the forces acting on the object. Well, we've done that in our big 6-step process earlier. So really, these are going to be the 6 steps from earlier. Okay, so you should be able to do those pretty quickly, no big deal. Okay, so once you identify all the forces on the object, now you can actually just draw a coordinate system. Right, so we identify our x and our y. Okay, and once we draw our coordinate system, we represent the object as a dot. Okay, so there's our dot at the origin. And then from here, we just start drawing all the vectors or all the force vectors for the forces we identified, okay? So maybe we identified a force this way, or a force this way, or a force this way. So that's the idea of a free body diagram. We're just going to collect all those force vectors that's kind of been all over the place. Once we have all that done, we're just going to sum the forces. And that's just going to give us our net force. And that's the last step. So this whole thing is just formalizing, doing some vector addition. Once you've done this, the rest of a problem, a force problem in physics, the rest is just a math problem. This is where the physics ends. Okay, so let's take a look here with just two quick examples. So an elevator suspended by a cable speeds up as it moves upward from the ground. Okay, so we know we're speeding up as we go up. As it moves up from the ground. Okay, so now we just have to identify the forces and draw a free body diagram. Well, here's my closed curve, my circle, and I know I have tension here. Okay, that's my contact force. And I also have this long range force, which is gravity. Okay, so I can just move over here. Okay, I've drawn my coordinate system. That's step number 2. Okay, and I've represented the whole elevator system as a point at the origin. And then now I just have to draw in those vectors. I identified 2, a contact force and a long range force. So now I'm going to draw my vectors. My contact force was tension. My long range force was gravity, pointing down. Remember, it says the elevator is accelerating, it's speeding up upwards, so that means my tension has to be greater than my gravity. Okay, so when I do my vector addition to get my net force, well, there it is. You can see that what's left over is just a little bit of the net force pointing up. That's what's going to cause our acceleration upward. Okay, so this is going to be the acceleration upward. All right, let's look at one more. So a tow rope pulls a skier up a snow-covered hill at a constant speed. All we need to do is just draw a representation of the skier, and we'll throw it all into a coordinate system and a free body diagram. All right, well, we have our motion diagram. Remember, it's being pulled at a constant speed, so all of these are the same length. Acceleration is 0. Okay, well, we can take that, move one more step, force identification. So for this step, we need to draw our enclosed circle. So we have the obvious. We have tension. Okay, that's what's pulling this skier up. Now we also have the normal force. Remember, I drew that in the previous example here. And we also have the kinetic friction pointing down and away from the motion, so it's going to point downhill. This is kinetic friction because this person's moving. And then the last one, because that's our 6th step from our last list, our last one is just the force of gravity. So now, next thing we need to do, we need to draw our coordinate system, which is here. Add our skier right in the middle. Now we just have to start drawing in all these vectors, okay? So from the origin, we have the tension vector. We have the normal force acting perpendicular to the ramp or the hill. We also have kinetic friction. And then we have our long range force, which is gravity. You'll notice that we do have this angle, which we can include here and here. So it kind of offsets gravity since we are going up the hill, but gravity always points downward. We can account for that. All right, and that's all we need to do for this example, is just identify all those forces. Now, just a quick summary. We've talked about different forces. We figured out how to identify them in a situation. We talked about Newton's 3 laws of motion, and we've talked about inertial reference frames, and we've done 2 quick examples of free body diagrams. So we'll do a lot more free body diagrams coming up in the next few lectures. So thank you for hanging in there. We've done something very challenging. We went through an entire chapter in pretty much one sitting. So I promise I won't do this much, but this is going to be a really, really good intro to what we're going to talk about for the rest of the week. So as always, if you have any questions or need anything, please let me know. I will be available.